This is my lab report for Lab 6 Magnetic Molasses. The purpose of this lab is to gain a deeper understanding of magnets and how the forces exerted between magnets and conductive metals occur. The fundamental physics principles that we use in this is the magnetic field of a dipole formula, the magnetic flux formula, Faraday's law, and also force on a wire. We found the average time of the falling magnet through the tube to be about 1.43 seconds, and that the magnet falls slower through the conducting tube due to current induced on the tube. And our system in this lab is the falling bar magnet and the aluminum foil tube. The surroundings is everything else around the magnet tube. And the initial conditions for our experiment includes the magnet starting from the very top of the tube and being dropped, and the time starts at 0 and counts up. So for the actual running of the experiment, a bar magnet is positioned above a conductive tube of aluminum foil. The magnet is then dropped into the tube and the stopwatch is started. The magnet essentially falls through the tube, and then once it falls out the bottom, someone catches it, and once the magnet reaches the bottom of the tube, the stopwatch is stopped, and that time is recorded, and the video is analyzed to find the specific time of how long the magnet was in the tube. And this is a picture of the experiment with the magnet being dropped into the tube, and also finding the north and south of the bar magnet. So for measurements and calculations, we have the dipole moment of the bar magnet from a previous lab, which was 1.2522, the radius of the tube to be 0.75 inches or 0.019 meters, the thickness width of the aluminum foil to be 0.02 meters, and for our experiment fall times, we had 5 there, and then the average time ended up being the summation of all those times divided by 5, which gave us an average of 1.3 seconds in the tube. Potential sources of error for our lab included bad lab equipment and materials, human error in recording the video and observations, frames per second of the camera not being precise enough to get an exact second measurement, and the non-uniformity of aluminum. This is the computational model. You can see we start with all the constants for the equation, and then a bunch of constants regarding the width and height of the tube and the radius. There is part of the code that's creating all of the different rings of current in the tube, and then also the bar and how it is represented with a magnetic dipole moment and the magnetic dipole moment vector U. We have two functions. The first function from a previous lab where we're calculating the magnetic field, and then also another function to calculate the d flux dt by first calculating flux and then dividing it by first calculating flux and then taking the derivative, which is done there. And then we have our for loop going through as the magnet goes through as the magnet falls through the tube, how each of the rings of current individually is affected. And then we also have at the very bottom the net force exerted on the magnet and how the bar's velocity and position changes as it falls through the tube. So this is what the computational model looks like, and from the red at the bottom, when the computational model is running, that red is actually traveling down the tube as the magnet falls, and you can see that according to our computational model, the total time the magnet spends in the tube is 1.195 seconds. And the difference in times between our experiment and the model was 0.235 seconds. This difference could be caused by errors in human calculations and lab equipment, or deviations from the values put into the model in terms of measured quantities. Our additional questions: if the resistivity of the conductor was as close as possible to 0, then the conductor would be a superconductor, and the EMF would essentially all translate into current, and this would make the force on the bar magnet so much larger that the magnet would essentially just stop falling it would not be able to fall through the tube. And also, if holes or slots were cut into the tube, there would be less rings of current overall, and so the net force on the magnet would be smaller, and so the magnet would fall through the tube faster. And in conclusion, we have gained a deeper understanding of how a bar magnet can induce a current in a conductor, and how these forces can affect the motion of the bar magnet. Thank you.